So, all of
All right. So, hello everyone. Can you hear me? Hi everyone. Um, my name is Jayakody, and I'm here to present our paper on part orientation use shape optimization for 3D printing. I'm sure most of you have seen 3D printing, and some of you have probably used 3D printers. So, when you use commercial 3D printers, most of the time you need support structures to print overhang features of complex models. So here you can see um, the result of armadillo model, and you can see when you print the model, it requires lot of support structures, and at the end of printing, you need to remove the support structures. So all those support structures are important to prevent failures. It increases the print time and material waste. So one of the main challenges in optimization, the design optimization, is to find ways to minimize support structures. So to do this, we have several variables available in the design space. Now, for instance, you can change the part orientation and you can change the part geometry. In part orientation, the idea is quite simple. You take a set of samples on the unit sphere, for example, and then you can change the mesh orientation and you can find the best orientation candidate that minimizes the support volume. Because depending on the orientation, the support structure volume will be different. In part geometry, you can see a simple example again, which requires support structures for the original geometry, and you can change the geometry into a different shape, which requires much less support. But the problem you can see is that the deformed geometry is quite different from the original one. So this type of large-scale deformation might be inapplicable for these complex models. For instance, the Voronoi sphere and like the knot model and complex mechanical parts. So the idea is to find shape changes that are as close as possible to the original geometry. So when you think about the part geometry, it's quite important for 3D printing applications. For example, several local geometric optimization methods were proposed to improve the structural strength of the 3D printed parts. And there have been some cage-based shape deformation methods that minimize support structures. But you can see that those methods deform the shape globally. And there have been also other methods to improve the balance of the 3D printed parts. And there are lots of other applications of geometric optimization. So in general, these examples show that geometric optimization is quite useful um, to improve the 3D printing performance. Now, um, in general, the existing methods treat part orientation and geometry as separate variables. So the main question we have is to see if we can find the best, if not the corresponding pair of part orientation and geometry to minimize support structures. And the next question is, can we um, optimize directly on triangle mesh models, because the designers prefer to work on the triangle mesh models. So for this, we propose an alternating optimization method, which change the part orientation first, and then compute the geometric updates for that particular orientation, and then kind of repeat the process until we meet the termination criteria. So the idea behind this alternating optimization is quite simple. So we convert the joint optimization into a set of simpler subproblems. So before we move to the optimization, we need an objective function. So we, we define the objective as a combination of overhang phases and support structure volume. So here you can see a set of examples of part orientation optimization using different objective functions. So you can see what happens when you use support structure volume only. Uh, the number of phases. So even though the volume decreases, the number of overhang phases increases. So in our case, what we try to do is to minimize both the overhang phases and the support structure volume. So how we compute the volume is by projecting the phases onto the build plate. And from the graphs, you can kind of see our method is quite efficient compared to the Ray-based approach, and it gives a quite good approximation. Um, so the first step in optimization is the part orientation. So we use Fibonacci sampling to get the orientation candidates on the unit sphere. Um, so again, the idea is quite simple. We pick the best orientation vector that minimizes the support proxy function value. And the users can pick different number of sample values. And here you can see the effect of sample values on the optimization time. So the next step is geometric optimization. Um, Here the idea is again simple. What we try to do is to um, project overhang phases onto overhang free configuration. So for each overhang phase, we compute an overhang free plane and then find the difference between the current phase and the target phase through a rigid transformation. So that provides the phase level change, as you can see. And then for the vertex level change, we propose a salient feature aware projection method. The idea is to minimize deviation in salient regions, salient but overhang regions. So if you look at the full shape energy, it's a collection of few energy terms. So the first one is the projection energy, which is the difference between the current vertices and the projected vertices. Um, and if you look at the smoothness energy, it helps us to ensure the vertex deviation is smooth. And then we add the support volume as well. We have several termination criteria, but the main one is the deviation from the original geometry. And you can see the shape change between the original and the optimized one is quite smooth. And also depending on your 3D printer, the overhang angle might be different. For example, if you use a high-end printer like Bamboo, FDM printer, you can print up to 60 degrees of overhang angle. So here we show that our method can be run with different overhang angle thresholds. And if you look at the results, first we present the alternating optimized results. So these have been optimized using orientation and geometry both. So you can see the difference between the original and the optimized versions of the armadillo. So there's a significant difference between support structures. And this is the knot model, which is a quite complex one. And again, you can see the difference in the support structures. Yeah. And then our framework can be also used as a geometry only optimization. So which means we take out the part orientation, but simply use the geometry. Choosing between these methods depend on your part and its complexity. For example, for models like these, hygienist models, alternating method performs better because it helps to reduce support under lower deviation. Um, so you can also see some sort of difference between the support structure volume between between the geometry only and alternating optimized versions. But in general, both the methods are effective in producing support structures. So for models like Kitten with a flat base, users prefer the geometry only optimization. So we have the original one and the optimized one. And again, you can see the difference between the substructures from the clean models. Um, but again, you can see the effect on surface feature distortion. If you look at the optimized version of our model. So to minimize this effect, you can fix the important regions of your part. For example, the functional parts of your functional regions of your part. Um, so for instance, in this example, we fix the face and the base of the Venus model before the optimization. And as you can see, it helps to minimize the effect of surface feature distortion. From the right-hand side, you can see um, the printed versions of the original and optimized versions. And if you look at the print times and the weight, you can see our method is both applicable to different support structure types. So in summary, we propose an alternating optimization method to find the best pair of orientation and geometry for 3D printing. The main advantage is our method is effective for a range of complex models, and our method can be used directly on triangle mesh models. Our method is also quite fast, and you can see the results from our paper. So one of the main limitations is, as I showed you earlier, the surface feature distortions from the projection method. And it can be quite challenging to optimize high resolution mesh models using this method because it increases the size of the linear system. Uh, yeah, but these limitations have been addressed by our recent method. So I will take 2 minutes to explain that as well. So in the new method, we learn the shape deformation through a neural vector field. So the difference compared to the previous method is that in this method the shape change is differentiable and continuous, and we also introduce a close-to-fine optimization method to efficiently optimize high-resolution mesh models. And you can see the difference between the original one and the projection based method in our paper and the neural shape. So you can see the face features have been preserved in the neural shape. So for those who are interested, I invite all of you to have a look at the paper. So thank you.
So all of the focus. Thank you, boss. But you can you take into account some physical constraints transition no results.
Uh,
Thank you.
yes. So actually, this is one of the of one of the next steps that we can consider in the optimization. But to have that physics constraints, we might need to extend for like a full polymetric model to find the like the finite element computation. So that can be one of the future steps. Yeah. Thank thank you for this. Yes. No, no, no. Sorry. No, so the we compute the normal support structures only. Um, So right now the for the optimization for the proxy function, we only use the normal support structure types, but for just to show that it's effective. Uh, Trace of the types, we just show some examples, but it's not guaranteed. So because we are not using
But in numbers, it's also reduce that to fit.
reduce that the thank you.
Maybe also last question is no one. Uh, so yeah, regarding the damage one is when you do the support phase, so basically what you do is you roll it and then you graduating it basically at the calls that and you generate more and or that you presented just now that then how do you think in case we need to expand just measure expand another order line? So what is your expectation in terms of because each one is very different. Yes. Then what may be the major obstacle in terms of the computation?
For instance, I think we can have like a differentiable summation of the results types, for example. So then we can integrate into the optimization and then run to the same pipeline. So that the future steps.
Okay. And also because, for example, like there are also other requirements where we normally generated the supports. So sometimes certain circuits we don't want to touch because those are the critical circuits.
Yes.
And also in another case we want this support only touch on the base. That's it. We don't want to have the base on other part. So that is something can be considered tonight.
We haven't really thought that, but yeah, maybe I'm not very sure as well, but yeah.
Okay. So I don't know. So is that something the direction that working towards?
So like what kind of parts are you?
Yeah, because right now we're saying that this volume is fair, the most traditional
Yeah.
there are so many types and so many options where we generate.
Yeah.
Right.
So I think like for example in neural shape method we don't use any kind of like for volume. We use the overhang phase as a variable, and then we show that we can actually minimize it by completely reduce constructions like overhead phases because overhead phases generate constructions. So if you can get rid of the overhead phases, then you have to get rid of volume. So so I was my answer. Focus on the overhead phases. Maybe not touch the
Thank you. Thank you so much. If no other questions, then yeah, let's thank the speaker again. So the next presenter is Lucas Vergez, and he is going to present lifetime-based generated design of 3D printed bearings. Why is setting it up? I just want to ask again whether the authors or presenter for the third paper is here. So I guess we guys another 7 minutes. Okay, yeah. Yeah, the floor is yours.
Thank you. Yeah, so um, today I will present my work about lifetime-based generative design of 3D printed bearing. I did that book with here, and I am currently in postdoc in Concordia University in Montreal. So today I will present a work that have some motivation. the basic motivation was that bearing is an ubiquitous mechanical standard component present everywhere. So basically, from a motor to a wheelchair, and basically every system that have a wheel in the world have a bearing inside. This is a really standard component made in often steel, but sometimes supply can be severely limited because of the environment, because of the context, because of a lot of things. For example, the space, for example, during pandemics, sometimes it's not possible to just deliver a bearing somewhere. So we want to develop something to replace that kind of bearing temporarily in order to make and manufacture directly the bearing from his own 3D printing, 3D printer. So here is the research problem. How to develop a fully 3D printable bearing design methodology designed to be manufactured locally with affordable printer, because we wanted to make it with the more affordable printer, the basic one made with plastic and PLA. We wanted it to be assembled on site without the need of a complex tool, for example, without any assembly, without any screw, without any nuts, for example, and adaptable to local constraints. So we have special constraint. We want an optimized design that maximize the lifetime of the bearing. So that was the research problems, basically how to make a design of a bearing that maximize the lifetime, but being in PLA, 3D printing with affordable printer. So here is the research problem. For the state of the art of in the literature, there is a lot of paper on classic steel bearing lifetime reduction. Of course, this is a really studied field. It's for a long time. It is studied the lifetime prediction of standard component like bearing, but it is always still bearing. There is no design optimization. I mean that the geometry of the bearing is really standard and always the same. So it's really the lifetime is really predictable, which is really different when we 3D print it. There is another field which is classic steel bearing design optimization. It is also steel bearing and with very limited geometry. For example, they just focus on the inner ring, inner race, or outer race of the rings. This is a really limited geometry deformation because of the manufacturing process, because we want it to be ball bearing and really manufacture easily with steel. So that's why the design optimization is as a really small design space. And now for a few years, there is 3D printing during experimentation. Some people generate some new design and try to experiment and try to measure the lifetime of the bearing and measure how it failed and how at what time. But there is no design optimization of it. They just test design directly and no lifetime prediction. So that was our goal, to make some methodology that can predict the lifetime of the geometry and optimize the geometry to maximize the lifetime. So at the basics, we test a lot. We design first test bench and test rig with a motor to test all the bearing and measure the lifetime of bearing and the radial load. And actually, it was quite surprising that there were more than one type of failure that can exist. There were blocking failure, which is basically the internal rotation of the roller that can block together and block the rotation. And this is not really fail as the bearing doesn't break. but it's blocked the system, so it's considered as a failure for us. There is the breaking failure, the most famous, just the roller breaks during the rolling, and then the dislocation. It means that the roller goes out and escape from the rings because the geometry is too flat. So the overall idea of this work is that for each kind of failure, we created a score associated of a geometry that is used to predict the lifetime. And then we correlate the lifetime with the experiment, with the score that we designed. And with that, we created a design space for building construction. Like this, we were able to optimize the geometry in the design space to maximize that lifetime. And then we get some results of optimized geometry, and we're able to compare it to state-of-the-art geometries. So I will go through all the Thomas-Seale failure and say how we designed the score for the geometry. So for this collocation failure, the problem is when the roller escaped from the inner and outer ring. So for that, we just take into account something that we call the science abrasion field, which is basically just a sign distance field, but in one direction. Because as our roller are always in the real shape of revolution, so we can simulate it. Just go through through this portion of the thing. And we tried to simulate the abrasion of the plastic during the experiment because there is a decreasing of the plastic during its fall, and we simulated it with that oriented silent distance field. And like this, we can create a field that represents the collision of between the roller and the rings. And like this, we can measure the dislocation of the roller to the ring. So how we measure that? Basically, we make a path for the inner ring, and we try to make a path minimizing the collision between the three components. And we see the minimal energy of collision that it takes. We designed the score based on that maximal energy, which is 1/1 plus the energy, because we want it to be between 0 and 1, and the Bailin geometry has a score of 0. So that is for the dislocation failure. I will explain later how to modelize the lifetime. For the blocking failure, this is a bit tricky to explain, but this is an internal rotation because there is clearance between the components, so there is an internal rotation of the roller. And when it rotates, it's blocked together. But first of all, we have to know if this rotation is feasible or not, and we will quantify how the roller can rotate in that direction or not. So like this, we can just rotate the roller until collision with the other ring. And for example, with convex geometry like the geometry, we have 90 degrees of rotation. It means that the roller can completely rotate internally without any collision, so it means that it will block directly because of it. So that's not a good geometry, and we prefer the bottom geometry that's shown here. To see if it will block or not, we have first to measure the distance between the two rollers in function of the rotation of the two rollers and also the clearance between those two. I will not explain how to measure the distance, but here it is. And the problem here is to see if the point zero is a local minimum. I explained. We want the bearing to be to be stable when the two rollers are exactly at zero location. Because when they are not rotated, we want the bearing to be stable. So we don't want the roller to rotate automatically. So when we have the graph of the distance between the two rollers and the orientation of the two rollers, we want it to be stable at the 0 point, so it means that we want the 0 point to be a local minimum. And like this, we can directly check this with the by verifying some trajectory in that surface, and then create the blocking score, which is proportional to that local minimum. So how to escape from this score or not. And the harder it is to escape, the better it is for the baby. That was for the blocking score. For the breaking failure, this is way easier because this is the most studied failure in the literature. So we can first simulate the maximal stress in the roller thanks to Earth's contact. And then we have the relationship between maximal stress and lifetime that follows Weber law, because this is how it is today in classic steel bearing, and we reproduce it to plastic bearing, considering that it will follow the same mechanical rules. Adjusting all the coefficients. Actually, as we will see later, it works pretty well. So that's how we designed our score for breaking. So now that we have all these three score, we can modelize the lifetime of a bearing. For this, we test a lot of bearings in the test bench. We adjusted the coefficient considering that the equation would be in the type of the balloon with a weight and exponent, as the breaking failing before shown and previous experiments shows. And we made the assumption that all the type of failure follows the same types of equation. So we have the coefficient W and N, which is to modelize the lifetime. But we have also two other coefficients, which is eta and beta, and they are for taking into account the probability of failure, because we cannot predict exact lifetime duration of bearing. We will predict a distribution of probability of failure, because it will not fail at each number of cycles each time. So that's why we have these other coefficients, eta and beta. And for which we did a lot of tests to adjust those coefficients. To illustrate the fact that the probability of failure is important, for rolling profile, the given probability of failure, we can get the number of cycles before failure. Then, for example, this kind of shape of roller, we have this type of graphics which shows the cycle of failure given the probability of failure. So we can see that given different probability of failure can give a different number of cycle of failure before failure, of course, but also can change the type of failure. So it means that the ranking of the profile can vary depending on the probability of failure that we want. So we will set it at, for example, 50% or 90% and set it and do the optimization given that probability of failure. So the design space definition for this bearing is just this line curve done with some control points. It is the blue curve to the left. And given this control point, we can get the busy curve and we apply the symmetry, order symmetry, and get the remotion of the rig and the rig. We get the complete geometry of the rig in order to make it after. And we can get the exact number of roller in the bearing by adjusting some measurement. Basically, this is the distance between the z-axis and the center of the bearing. And by adjusting this length, we can exactly get exact amount of number of roller because it must be taken. So anyway. The design space definition have some constraint, design constraint, for example, the minimal thickness of the outer ring, the inner ring, and the minimal thickness of the more. Done with experiment, because if it's too thin, it means that it will break even before beginning to roll. Also, there is the maximal angle of the printing, which has exactly what the previous presenter said. So we have to get this spline to respect that constraint. So we set all the values at the bottom. And now that we have everything, we can begin to optimize the geometry. So we create a curve with busy coefficient. We simulate all the lifetime coefficient we found experimentally, and then we get the minimal lifetime given the 3 lifetime that we get, and we just take the lifetime, the power default with the best lifetime, and then apply a genetic algorithm in order to optimize and maximize the lifetime. So here are the results. We saw that blocking failure encourage flat surface, which is quite normal because it means that it will be stable when both roller will be in correct position. Dislocation encourage radius variation because it will be less dislocate when it has a lot of variation, and breaking encourage large minimal radius. So given all that, at the end, we see that the best types of roller geometry is things like the blue one at the top. And the state-of-the-art bearing was tested on the test bed and the Hyunyoung nodes in order to compare. And we multiplied by 20 the average lifetime of the bearing. So actually, that's a lot. The limitation of this work is that we consider only pure radial force and no axial forces, which can vary a lot the type of failure. It's only revolution, and we consider contact over all the lengths of them. So that's why the future works focus on large design space with gear bearing, which is also a really encouraging design without any revolution or that like this we can explore widely the design space because additive manufacturing opened a lot of doors in the design space to a lot of geometry. So yeah, thank you for your attention. Questions? Yeah.
Very nice talk. Thank you. So are all rollers online, or does your framework also support maybe component rollers or even
Yeah, by congruent, you mean contact between the
geometrically identical rollers?
yeah, they are all identical. Yeah. For now, they are all identical because, of course, the maximum radius must be the same in order to be in contact with the inner and outer ring. But that's and also I'm just thinking at the same time. I think that if the geometry of the curve differ, it means that sometimes there is no contact with the outer ring or the inner ring, or
maybe still be in a contact, but maybe for this blocking, you have two different geometries. I help a bit in this block point.
Maybe I don't see what you mean by congruent geometry.
If you have identical geometries, you have certain condition to avoid blocking. And if you have, let's say, both rollers of different geometry and even of different geometry, you have kind of not just a single profile, it's a particular optimization, but you have two profiles, two rotation shapes.
Okay. For now, the methodology doesn't allow that kind of shape actually, but it could be another feature works to work in, even if it's revolution shape here.
Thank you.
Thank you, very interesting part. So your material is plastic. Addition, what if we do additive manufacturing with metal? That's also possible these days.
I think it would be really interesting, and I think the methodology can be transferred to metal. We didn't test more actually, but I think that everything we made, we took into account the clearance and everything. So I think with metal, the clearance will be maybe wider or maybe not. The coefficient will be different. So I mean, the interesting part will be here. All the coefficient will change with metal. But I mean, all the other cities, the type of failure, maybe the failure will differ. Maybe but I think that theoretically it shouldn't change. So everything can be transferred to metal manufacturing, and it will be also really interesting because it means that the lifetime will be way bigger. But the controversy is that it's not manufacturable everywhere because metal additive manufacturing is key. So that's why we choose to focus on PLA, really cheap material.
So it seems to me that you utilize genetic algorithm. Yeah. So right now, even commercial software has lots of generative algorithms. Did you try others?
Other optimization, we tried. We found that the best one was a classic genetic algorithm. Also, it's very common. We use genetic algorithm for generative design, and it fits very well because we have to explore really different geometry and go deeply into that kind of geometry. And also, when we do mutation and crossover between geometry, it means that the best geometry will be between the best. I mean,
so you penalized designs that doesn't satisfy your knowledge.
Yeah. No, I didn't analyze. I just cut it off. So I didn't took into account the design that didn't respect our constraint. So that's why I showed just the first generation is the generation 3 because the 1 and 2 is out of constraint, so they was not even shown.
Thank you very much for your presentation. Actually, if I were back to do metal print, roller lyrics in the future, so it's very interesting for me to see this. One question I have is considering the lifetime, have you thought about the beer properties of beers? Because especially by plastic, I think a beer might be quite drastic, but also in France, for instance, of
I'm the
okay. So, sorry. Did you get the question?
are you talking about the lubricant?
Yes.
Yeah. No, we wanted to be the as a first study on it to be the simplest way. So without lubricant, with the cheapest material, with the cheapest printer. That's all. So we didn't try the lubricant because also the thing is that it's really hard to do a waterproof cage in 3D printing. So that can be movable. So that's why we discard this solution, even if we can put some lubricant, some grease without any waterproof cage, but it means that it will escape, and at one point it will just live a longer life. We just made the assumption that the best design, the optimized design in the dry experiment will also be the best design in the lubricant environment. But maybe that's not true, and that's why we have to do further experiments.
Okay, I have a question. So very interesting book, the work. So I'm wondering, did you try like a bearing model to print by using some commercial 3D printer at the any cubic or any others? Because that my son by chance to print some bearing models by using some commercial 3D printer. Looks like there is no challenge like what you show. For example, like the blocking, breaking, or dislocation. So I'm wondering, is there some challenges because we are working on some very spatial bearing model? I'm just curious.
You think you mean is the constraint will change if we change of 3D printer?
No, I mean, for example, we download some bearing model online and use in commercial 3D printer. Yeah, they can print.
Yeah.
And seems no issue. Yeah. I'm curious because your bearing is more practical and realistic, or I don't know. Yeah, it looks like.
Yeah, but it's not just about lifetime, right? If this left the bearing, it revolves during 100,000 cycles. So it means that it rolls a lot. But it's nothing compared the optimized geometry. I don't know if it's answered, but I mean, if you just it's not optimized data. If you just printing a sphere with a 3D printer, it will work, of course, but it will vibrate, do a lot of vibration, dislocate really quickly compared to that kind of geometry that doesn't have this kind of problem.
Okay, thank you.
Thank you. I guess the question is also related to which printer you use to print it, also like what condition you use to do the testing.
Yeah, so we did all our experiments with Ultimaker Cure because we wanted to be reproducible and we wanted to do everything with the same printer to be the more predictable and be comparable to the other. But we also, in my side, I did also the test with Anycubic, so with Creality 3D printer, and each time all the condition we have to set is the clearance. So it means that, and also the angle of printing, because there are some printing when there is less layer, we can have a better angle of printing. So these two parameters have to be set when we change the printer, but that's this is really easy to set in the framework.
Thank you. So